Now I'm going to look at the issue of false ceilings in the room of origin. So what is the impact when you've got a fire and heat and smoke rising if you've got a false ceiling in that particular room? How do you deal with that then? Because there may be situations where there is a false ceiling in the compartment being ventilated, and therefore what ceiling height do you apply? Now clearly, if the false ceiling is fully sealed up, well that's the ceiling height. But what happens if you've got half it cleared up, or what happens if you've got gaps between it? So this is what we're going to come on to now. Where there is an unbroken false compartment, it must be treated as the top of the smoke layer. Now, however, if the false ceiling is porous to smoke, in other words, it has an appreciable free area, any smoke screens forming the smoke reservoir must be continued above that ceiling. Obviously, it must be continued above that ceiling. Now, if the proportion of free area is large enough, the reservoir and its screens may be totally above the false ceiling. So you can actually have it above the false ceiling. Because what it's saying is, if it's got an appreciable amount of air, it'll just go straight through it. It will not have a massive impact on it. But you've got to work it out. Now, the permeable ceiling ought not to interfere appreciably with the flow of smoke from the fire to the smoke ventilation openings above the false ceiling. And the general rule of thumb is that you need at least 25% of free area. So 25% of the ceiling area must be free, must be open. Now, cool smoke can sometimes be expected to affect nearby shops, but however, it would not significantly hinder safe escape. So, don't forget to consider the impact of false ceilings when you're looking at your clear layer height and where you're putting your smoke screen. Now, the next issue I'm going to consider in step 11 is the issue of enforcement of the regulations with regards to smoke, heat and exhaust ventilation systems. Now, when a smoke, heat and exhaust ventilation system has been designed and any issues arise about what is acceptable or not, then the enforcing body who enforce the fire safety regulations will decide what is actually acceptable. Now, if this building is large or complex, it's unlikely that it will be able to meet prescriptive guidelines given in the relevant standards. And it's more usual for a fire engineered solution to be adopted in order to achieve a successful ventilation system in a building with very large compartments. Now, it is important that all the details are correct. If not, obviously the system is not likely to work. And any assumptions made and any calculation procedures which are correct for one scenario may not be correct for another. You've got to ensure the validity of any formula used. Some have parameters which say, for example, a small atrium, which do not apply to a large atrium. So any formulas used, you must make sure the validity of that. You know, some might be only valid for near plume, complex plume. Make sure they are valid. For example, when we determine the simple plume, you've got different models. You've got simple and complex plumes. You've got near field, you've got far field. You've got different coefficients in the calculations. Can you ensure that those calculations are correct? Because using the wrong formula can double or half the smoke that's being produced. And that will have a significant impact. You've got to make sure it's all valid. For example, you may find that a near field model is used instead of a far field and it will give a more favourable answer. In other words, a lower mass flow rate of smoke. Now that suits the designer, but that's not good for life safety, is it? In other words, you can't pick and choose the formulas you're going to use. You've got to make sure that's valid for the particular circumstances what you're using. Now, in order to design any smoke, heat and exhaust ventilation system, the designer's going to have to make a number of assumptions. And it's extremely difficult to design from first principles, so you've got to make some assumptions. But all that's important is those assumptions must be passed on to the enforcers and the building owners. You've got to pass it on. The biggest problem arises when an assumption is unreasonable. For example, if they design a shopping centre or an atrium anywhere and they're saying, right, well, you're going to use a 1.5 megawatt fire in the main area, on the shops, for example, 1.5 megawatt fire in the shops. Well, that's not reasonable. Where you get 1.5 megawatt fire for? Well, it's very favourable to our calculations. Well, it might be favourable to them, mate. You're not going to limit that in the shops, are you? There's no way you're going to get a shop. Well, the shops will not have that fire growth rate. You'll not have a 1.5 megawatt fire. It's unreasonable. Where do you get your design fire size from? In a shopping centre, for example, If it's sprinklered, you're going to get a 5 megawatt fire. If it's a fast response sprinkler, you get a 2.5 megawatt fire. Anything less than that, I want to see where the risk assessment is. Because if you design it on 1.5 megawatt, how are you going to maintain that standard? Yeah, it's not reasonable. For example, again, in the atrium, if you're going to design an atrium, a massive atrium, and say, we're going to make it totally sterile, we're going to assume a 1 megawatt fire. The biggest problem is, how do you manage that now? How do you make sure no one brings anything into that atrium? So again, this must be specified and must be passed across to the end user. Now, the enforcer may also not be able to follow all the calculations, but at least they'll have a judgment call on the assumptions. In other words, that's a good assumption. The enforcer must be aware that in most unusual and complex buildings, more expertise may be required. So you do have to do that.